Hello everyone, and welcome to this SoCS masterclass on domain-dependent and domain-independent heuristic search. I hope you're all at home safe and sound and enjoying SoCS so far. My name is Roni, and I'm a principal scientist at the Palo Alto Research Center and also a faculty member in Ben-Gurion University in Israel. During this talk, you might notice I change a bit. If this happens, I suggest you take a break and get a nap. On a more serious note, in this talk I'll show you that heuristic search is in fact an extremely general domain-independent problem-solving framework. It can be applied with appropriate modifications to a range of problems well beyond finding optimal solutions to puzzles. I'll start by covering some search basics and tell you about some non-trivial applications of heuristic search that I've worked on in the past. Then, I'll talk about one of the most important ways in which we can make search algorithms scale, which is to trade off solution quality for runtime. I'll introduce several forms of suboptimality, including bounded cost search, anytime search, and probably bounded-suboptimal search. I tried to make this masterclass as self-contained as possible, so I hope this will be enjoyable and useful to all who are interested. If this is the only masterclass you've attended, a search problem can be defined by an initial state, a goal state, and a set of state transition operators. A solution to a search problem is a sequence of such operators that gets you from a start state to a goal state. The basic action most search algorithms use to solve search problem is called expand. Expanding a state means applying all possible operators to that state, revealing which state you can get to from that state by applying a single operator. Search algorithms work by executing many expand actions, meaning expanding many nodes, many states, until a solution that is sufficiently good for us is found. This masterclass focuses not just on any search problems, but on heuristic search problems. In a heuristic search problem, we are also supplied with a heuristic function. There are many ways to define what a heuristic function does, but the most common one in heuristic search is that a heuristic function is a function that accepts a state and outputs an estimate of the cost of getting from that state to a goal. If there are multiple goals, the heuristic will try to estimate the cost of getting to the closest goal. If that heuristic is lower bound on the actual cost, it is called an admissible heuristic. It is common to explain search algorithms on neat, well-known puzzles like Rubik's Cube. The initial and goal states are the initial and desired configurations of the cube, and the operators are ways to twist the cube. But I want to highlight that many problems are naturally described as search problems, and therefore can be solved by heuristic search algorithms. In fact, standard domain-independent planning problems expressed in strips on PDDL or other planning languages are in fact heuristic search problems, especially since there is already a huge body of work on how to generate heuristics for these domains. One current search problem that has received recent attention is in automated warehouses, where one wants to move box-carrying robots from shelves to distribution depots. Here, the start state is the current configuration, current location of the robots, and the goal is where we want the robots to go to, and the operators on how to move all these robots. Heuristic search algorithms are currently at the state of the art in solving such problems. The fact that search is a general problem-solving technique has been acknowledged from the very early days of AI, even in the famous general problem-solving problem by Newell and Simon. If I can quote some part of their seminal work, their general problem-solving program operates on problems that can be formulated in terms of objects and operators, and the problem for them is when the problem solver wants to achieve some desired state. So exactly, goal state and operators, just like our search problem. Just to stress the point a bit more, here are some perhaps less well-known application domains in which I have applied heuristic search. Let's start with searching for friends in social networks. There, the operator was to crawl to some profile in a social network and acquire some information about it. And the state was the subset of the social network we already acquired information about. Another application is to find central nodes in a graph. There, the set of graph node that we consider the most central is the state, and the operators are to add an additional node to this set. This problem has important application in network security. Searching for minimal diagnosis in faulty systems is also an important search problem, and it has been solved with heuristic search algorithms before. State there is a set of components that we assume are faulty, and an operator is to add an additional components to this set, meaning to assume that another component is faulty. When searching for efficient error correction codes, the state was a set of numbers that are already coded to bit vectors, and the operator was to add a new number and a new bit vector that is assigned to it. Multi-agent planning and multi-agent pathfinding are both applications in which it is very clear why there are search problems. The state is the current state of all agents, and the operators are all ways in which these agents can move. Lastly, I want to mention this application of heuristic search, which is how to recognize textual entailment. Textual entailment is a relation between two sentences which says that one sentence entails the other. The way to look at it as a heuristic search problem is to assume that the state is a sentence, and the operators are sentence manipulation actions that manipulate the sentence while preserving its meaning to some extent. For example, changing from active to passive, or replacing names with anaphoras. This problem also was solved with heuristic search. At this stage, I hope you are as excited as I am about solving search problems, because they're so general. The nice thing is that we already have domain-independent and very general algorithms to solve search problems. For completeness, let's recap some of the basics. Many such algorithms maintain a set of nodes called open or open list. These are the set of nodes that have been generated and we are considering to expand next. In this example, the open list are nodes A, B, D, and E. Also, many such algorithms also maintain the lowest cost path found so far from the start state to each of these nodes in open. This is denoted usually as the G value of the state. Now that we define G and H, we can explain the famous A-star algorithm. A-star says, in every iteration, expand the node in open that has the minimal G plus H value. Now, the basic theory of heuristic search says that if your heuristic is admissible, meaning it is a lower bound on the cost of getting to the goal, then once you've expanded the goal, then you know that you have gotten the optimal solution to it. In addition, under certain conditions, A-star also is guaranteed to expand the minimal set of nodes necessary in order to prove that you found an optimal solution. Now at this stage, if you haven't already, I strongly recommend that you watch Nathan Stutevant's masterclass in these talks on these conditions, and also on very recent and cool algorithms that can do better when these conditions do not hold. But let's simplify for our discussion and assume that A-star is indeed the best algorithm to solve such problems. This means something very profound. Search is such a general problem-solving method, and A-star is an optimal algorithm to solve search problems. Again, that's not super accurate, but close enough. But what this means is that all problems are solved. Everything can be defined, or many things can be defined as search problems, and we have the best search algorithms in the world. Not quite. First of all, A-star is designed to return optimal solutions. However, do we really want optimal solutions? If you can have an optimal solution in 3 hours and it's something that's almost optimal in 1 second, no. Often in many cases you would say, give me the solution fast. Who cares about that, some teeny bits of optimality? Also, the optimal effectiveness of A-star only means that it's optimally effective in order to find and prove that your solution is optimal. And often proving is much more harder than actually finding the optimal solution. So we might prefer an algorithm that finds the solution very fast and doesn't prove that it's optimal. And we can even check if it's optimal empirically in doing some statistics. It will not be a perfect proof, but it might be good enough in many cases. Again, because finding a solution is often much easier than proving that it is indeed optimal. So, in many cases, even A star is not fast enough. So let's recap. We have a search problem. One way is to take the search problem and solve it with A star or some other optimal search algorithm. There is another way, however. You can use non-optimal algorithms like greedy search, greedy best first search, genetic algorithms, simultaneous. These are all very fast algorithms. However, they do not give any guarantee about their solution quality. So you have a choice for your problem. You can solve it with an optimal algorithm and you'll get optimal, which is good, but it often will not be able to, you will often will not be able to scale to large problems. Or you can throw away optimality, but get the solution fast. What people usually choose, it's sad to say, is not to find the optimal solution. I know this is sad. But there is a price. The solution they get is unbounded. It can be horrible. But do not despair. There is a happy ending to the story. In this masterclass, I'll show you several middle grounds between these extremes of wanting only optimal solutions, sufficing with any solution. Bounded cost search is such a middle ground in which we are given an additional parameter C, and we are happy with any solution so long as it is under this cost-bound parameter C. This corresponds to setup when you have some kind of limited budget. Another setup, which is between these extremes, is anytime search. In anytime search, we do not know how much time we will have to run the algorithm. So we would like an algorithm that returns a solution fast, and then, if it has more time, improves the quality of that solution until eventually, if it has enough time, it converges to the optimal solution. Also, we'll show another setup which is called Bounded-Suboptimal search. There, we accept a parameter W, and we are happy with any solution as long as the cost of that solution is at most W times the cost of the optimal solution. And at the end, I'll show you another setup, which is called probably Bounded-Suboptimal search, which is very similar to Bounded-Suboptimal search, except that you have an additional parameter delta, and we're happy to find a solution whose cost is at most W times the optimal solution with high probability. So this will be our journey in the range between any solution and optimal solution. An interesting thing I will show you is that if you have an algorithm to solve bounded cost search problems, you can automatically get an algorithm to solve bounded-suboptimal search algorithms and also anytime search algorithms. And if you have an algorithm to solve anytime search algorithms, you can get an algorithm to solve probably bounded-suboptimal setup. Quite cool. But before we continue, let's take a short break. Thank you for coming back. We can finally start our journey in the world of suboptimal search. The high-level theme I'm gonna make is that in order to solve a given search problem, you really need to understand what type of solution you are willing to accept. And then you can make an informed decision of which search algorithm you want to choose. Because, really, search problems are not all nails. We will start with talking about bounded cost search problems and how to solve them. A bounded cost search problem is just like any other search problem. It has an initial state, a goal test function that defines which states are goals, and a set of operators. However, it also has a cost-bound parameter C, and the meaning is that we are willing to accept any solution whose cost is equal to C or less, while any solution to the problem whose cost is larger than C is totally irrelevant to us and we don't want to consider it. In addition, we will assume that we have a given heuristic function, which estimates the cost of getting from a state to the closest goal. And now the question is, how do we create a heuristic search algorithm that solves efficiently the bounded cost search problem? Bounded cost search is one of the least studied search problems in the heuristic search literature. This is surprising because bounded cost search is basically the satisfaction version of any optimization problem. And the cost bound, that corresponds to a limited budget of some form. For example, a limited fuel, or time deadline, or some confidence threshold. In all these cases, modeling it as a bounded cost search makes a lot of sense. There are several baseline approaches for solving bounded cost search problems. For example, you can use depth-first search and use the cost bound to prune branches that go beyond that bound. This can be very fast and effective. However, like other depth-first search solutions, the problem is that if you start going down some branch, you are committed to continue along that branch, even if other branches seem more promising. In other words, a depth-first search is not a best-first search. Another approach to solve bounded cost search problems is to compile them to a constraint program and then solve them with constraint programming solver. Modern constraint programming solvers are very effective. You can hear a lot more about this in Roman Bartak's masterclass in this SoCS on constraint programming. But one thing to note is that in order to use this approach to solve a bounded cost search problem, you need to first compile that problem to a constraint programming program. This is not always trivial. In addition, if you have some sophisticated domain-specific heuristic function, it is not trivial at all to tell the constraint programming solver to use it. Lastly, there is another baseline approach to solve bounded cost search problems. In this approach, we would use some optimal cost algorithms, such as A star, to solve the problem. Then we would look at the solution cost. If it's below the cost bound, then we can return it. If it's above the cost bound, we know for sure that there is no solution beneath the cost bound as required. The limitation of this approach, however, is that we expect that finding optimal solution would be much harder than finding a bounded cost solution in most cases, and we would like to exploit that in some way. Consider the following example, which will highlight why we would not like to solve a bounded cost search problem with an optimal search algorithm. Assume that in our search, we have now in OpenList two nodes, A and B, and we need to decide which node to expand next. So who would you choose? Okay, let me give you some more information. Let's assume you know that in the subtree beneath node A, you might find a solution whose cost is 120, and you might find a solution whose cost is 150. On the other hand, beneath node B, you might find a solution whose cost is 100, and you might find a solution whose cost is 200. At this stage, if you're looking for optimal solutions, you're better off expanding node B, because even if you find one of the goals under node A, you'd still have to expand node B to verify that it does not have a solution of cost 100 in its subtree. But what if I give you even more information? That under A, there is a 50% chance of finding a goal of 120 and a 50% chance of finding a goal of cost 150. And for B, it's also 50-50. What now? Which node will you choose to expand next? Still, if you want to find the optimal solution, you should always expand node B, since as long as there is some probability, even very small, that the solution of cost 100 will actually be there, you'll have to check this option before declaring any other solution to be optimal. So, if you would apply an optimal search algorithm in this setting, you would always expand node B, regardless of what is the probability of getting these goals. Now, assume we want to solve a bounded cost search problem in this same setting, but the cost bound is 160. This means if we go to find a solution with cost 120 or even 150, we would be able to stop the search and return happily that solution, because any solution under the cost bound is sufficiently for us. Now in this case, we may consider expanding node A, and not node B. In fact, under node A, we will certainly find a solution that is under the cost bound. So maybe A is preferable. I hope this example demonstrates that the decision-making process needed for bounded cost search is different from the one needed for optimal search. Next, I'll present the heuristic search algorithm for solving bounded cost search. The algorithm I'll present now is called potential search. It is the best first search that chooses to expand in every iteration the state with the highest potential, where the potential of a state is the probability that the optimal path passing through that state from the start state to the goal state has a cost less than or equal to the desired cost bound. To define this slightly more formally, recall that G of n is the lowest cost path from the start to n. H star of n is the way we define the perfect heuristic, which is the lowest cost path from n to the goal, and C is our desired cost bound. So now, with these notations, we can define the potential of a node as follows. It is the probability that G plus H star is less than or equal to C. Remember that we also have a heuristic, and while the heuristic may not be accurate, it is expected to have some statistical relation with the value at estimate, which is H star. Therefore, I'll correct the definition of potential above such that it also considers the heuristic. So now we know what is potential search. It is the best first search that expands in every iteration the node with the highest potential in open. But I didn't explain how exactly to compute the potential. A possible approach to estimate the potential of a node is to gather statistics about the relation between the heuristic value h and the value of the optimal heuristic h star. Here you see two such plots for two search domains, the key player problem in communication and the beloved 15 puzzle. The x and y axes are the heuristic value of the state and the perfect heuristic for it. These plots were generated offline, so we had time to compute the perfect heuristic for all sample states. The red dashed line is a linear fit over the data points. As can be seen, the linear fit is not horrible. For the key player problem, it's quite accurate. But for the tile puzzle, we see an interesting phenomenon. Roughly, the difference between the h and h star increases with h. This phenomenon has been observed in other domains as well. You can see here the same plots for the Bloxwell domain and also for Frisell. Again, roughly, the same similar phenomena. As you increase h, the noise you get for H star grows larger. We characterize this phenomena by defining a heuristic error model that we call the relative linear heuristic error model. In this model, the optimal path from a state is equal to its heuristic value times alpha, where alpha is some random IID variable. Visually, this corresponds to having a larger error for larger heuristic estimate, which makes sense in many domains. This heuristic error model has two useful properties. First, under this model, the state with the highest potential is actually the state with the lowest c minus g divided by h value. Informally, the idea behind this weird function is that the denominator is an upper bound on the relevant h star values before we go out of the bound, and the denominator is a lower bound. More importantly, using this theorem, we can now implement potential search. We can simply run a best first search using this c minus g divided by h function. This is quite neat because we can run a potential search without directly computing the potential. Second good thing about this heuristic error model is that we actually tried it and it worked quite well. What you can see here in this table is the percentage of nodes potential search with this model expanded out of all the nodes A star would expand. And you can see this for different cost bounds, which are shown in the columns 55, 60, and so on. You can see that as we wanted, potential search is able to be much faster than A star and gain even more speed as we increase the cost bound, which makes sense because higher cost bounds means easier problems. Good. This is all I wanted to say for now about bounded cost search. For now, let's move onward to anytime search. Recall that an anytime search algorithm is an algorithm that returns a solution quickly and then continues to generate solutions as it is given more computation time until the algorithm is either stopped or until it converges to an optimal solution. Now here is something super simple but neat. If you have a bounded cost search algorithm, you can use it to create an anytime search algorithm by following this simple pseudocode. Initialize the incumbent best solution cost to infinity. Then run a bounded cost search to find any solution with a lower cost. Then update the incumbent best solution with the newly found solution and continue this process, setting in every iteration the found solution cost as the cost bound for the next iteration. And that's it. If our bounded cost search algorithm is good, then it does exactly what we'd like an anytime search algorithm to do. It tries to return a better and better solution as quickly as possible. Now, if you solve this bounded cost search problem with potential search, you get an algorithm that is called anytime potential search, APTS, or anytime non-parametric A star. We implemented and tried this algorithm on two robotic arm domains and the multiple sequence alignment problem. The results are shown in these three plots. The x-axis is the time, and the y-axis is solution quality. As you can see, anytime potential search is not always the best algorithm, but it provides a very anytime behavior. That is, it provides fast changes to the incumbent, which is arguably a desired behavior for anytime algorithms, as they do not know when they will be halted. It is worth noting that the other lines in these plots corresponds to the famous anytime repairing A star algorithm, which is a very effective algorithm in many cases. It works by running weighted A star with some weight, and then when a solution is found, it decreases this weight by some delta and continues the search. While we can see ARA star is sometimes better, using it is harder than anytime potential search because it requires defining this delta weight parameter and also the initial weight, while anytime potential search does not require any parameter. This is why it is also called anytime non-parametric A star. To summarize, we saw an algorithm to solve the bounded cost search problem, namely potential search, and we also show how an algorithm for bounded cost search can be used to create an algorithm for anytime search. Next, we'll discuss a common form of optimality called bounded-suboptimal search. I'll show several ways to solve bounded-suboptimal search problems and how bounded cost search algorithm can create a bounded-suboptimal search algorithm. But I think this is a good time to take a break. Thank you for joining back. And let's continue our journey in the land of suboptimal search. And now we'll focus on perhaps the most natural form of suboptimal search, which is called bounded suboptimal search. And we'll show how it relates to bounded cost search. As a reminder, bounded suboptimal search means that you have an additional parameter called W, and the objective is to find any solution whose cost is at most W times the cost of the optimal solution. It is important to note that the problem solver do not know the optimal cost when he is running the search. So we need to find a cost who is bounded by the optimal solution cost without knowing the optimal solution cost. Quite cool. Now, I want to focus on two high-level approaches to get a solution for a bounded suboptimal search problem. The first is called classical best-first search, and the second is called focal search. In classical best-first search, which was first introduced by Ira Paul's seminal work on weighted A-star, we basically run an A-star search, except that instead of expanding in every iteration the node with the minimal g plus h value, we use a different cost function, which we'll call f. This cost function is chosen such that, on the one hand, we search faster than A-star, and on the other hand, we guarantee that when the goal is expanded, the solution cost we get is at the most W times the cost of the optimal solution. In focal search, we take the set of nodes in open and extract some of them into a set that is called focal. And then, in every iteration, we choose one node from focal to expand next. So again, we define a subset of the nodes in open called focal, and we then use an additional heuristic to choose from this set of nodes which one to expand. Kim and Pearl were the first to introduce this framework in their seminal work on A-star epsilon. What I did not explain yet is, in the classical best-first search approach, how to define this f cost function. I did not explain how this focal is defined and also what is this focal heuristic. But don't worry, I'll do that now. In the classical best-first search approach, we want to define this f function in such a way that will guarantee that when we expand a goal state, we are guaranteed that it will return a solution whose suboptimality is indeed bounded. In the weighted A-star algorithm, this is done by using g plus wh as an f function. However, recent work by Nathan Stuttervant and his group characterizes a wide class of other f functions that can be used in classical best-first search framework and still yield an effective bounded suboptimal search solution. Luckily for us, Nathan is explaining these details in his masterclass in this very SoCS. So if you haven't watched his masterclass yet, I strongly recommend you do. Now, let's talk about focal search. The focal in focal search is designed to focus the search towards states that may satisfy the suboptimality bound. To define focal in focal search, consider first what does g plus h mean for a node n in open. It is an estimate of the cost of a solution that goes through n. If hn is admissible, then g plus h is a lower bound estimate on the solution that goes through that node. So, since open list contains at least one node that has the optimal solution under its subtree, it follows that the minimal g plus h in open is in fact a lower bound of the optimal solution cost. We will denote this lower bound by f-min and define the focal as all the nodes in open whose g plus h value is smaller than or equal to w times this f-min. To understand this, consider a node in open that is not in focal. That is, its g plus h is larger than w times f-min. Even if this node is in fact a goal state and we expand it, we still would have to expand at least one more node in focal, because otherwise we would not be able to guarantee the desired suboptimality. This is why focal search algorithms limit the selection of which node to expand to only nodes in focal. Note that every time we expand a node in open, two things may happen. First, new nodes may enter focal because the expanded node generated new nodes. But also, when we expand the node, we might cause an increase in F-min. This would change focal and would add more nodes into focal. To be more accurate, F-min might also decrease. However, we can always store the largest F-min we observe during the search and use that as the lower bound on the optimal solution cost. A powerful aspect of focal search is this secondary heuristic, because it can be anything you'd like. For example, it can be an inadmissible heuristic. And inadmissible heuristic are often more accurate than admissible heuristic, because admissible heuristics are biased to be a lower bound. For example, Thayer and Rummel proposed a bounded-suboptimal search algorithm called Explicit Estimation Search, or EES. EES is a focal search algorithm that uses a sophisticated combination of two types of heuristics, one that estimates the number of steps to reach a goal, and the other one estimates the cost of getting to the goal. And also, EES learns online the error of these heuristics and corrects them accordingly. Quite cool. The notions of focal and F-min can be leveraged to create a reduction between bounded cost search and bounded suboptimal search. You start by setting F-min, as I explained before. Then, you run a bounded cost search algorithm where the cost bound is W times F-min. If that search finds a solution, wonderful, we know that this solution satisfies the desired suboptimality bound. However, if during the search F-min increases, we modify the search so that the cost bound now is W times the new F-min. This would require shuffling open again. However, this may be done in an effective way using smart data structures. We implemented this approach, and as the bounded cost search algorithm, we tried, you guessed it, potential search. And the outcome is an algorithm that we called dynamic potential search, or DPS. DPS does all that I explained now. So the bounded cost search algorithm it runs in every iteration is basically a BFS with W times F-min as the cost bound, using this evaluation function, which if you go back several slides, this is exactly the potential search function, just replacing C with W F-min. The interesting thing is that we're using here notions of F-min and focal, but actually what is run in practice is a classical best first search. It turns out DPS works quite well on a range of domains. What you can see here is results from different puzzle domains, where the x-axis is the desired suboptimality, and the y-axis shows how many problems were solved under some fixed time budget. So higher is better. Looks good, right? DPS outperforms all algorithms in almost all cases. Neat. However, there are also some other domains. In these domains, as you can see, DPS does not amazingly. And the question is why? Why DPS works well in some domains and not in others? This is an open question. We don't know. However, we have some hypotheses. One of them is that potential search only tries to maximize the probability that a solution would exist in a node under the cost bound. But it does not think about the search effort of finding that solution. And integrating that would be an interesting feat. Another thing is that potential search, as we implemented it, assumed the linear relative error model we talked about before. However, the heuristic error model in practice can be quite different. For example, what you can see here is different plots of H versus H star on a range of domains. As you can see, the behavior of the heuristic varies significantly. It would be interesting to learn an intelligent potential function or some other function that would consider this information. So we saw that having a bounded cost search algorithm, like potential search, allows us to create not just an anytime search algorithm, but also a bounded suboptimal search algorithm. I also mentioned before very briefly EES. EES is not a classical best first search approach, but it is a focal search. And it is worth mentioning that it is possible to adapt EES to create a bounded cost search algorithm in an algorithm called BEES, and also to create an anytime search algorithm in an algorithm called AES. And as I said before, it is not clear which of these work better. But it is nice to see that these two approaches, classical best first search and focal search, have variants for bounded cost search, bounded suboptimal search, and anytime search. Now we are ready to get to the final part of this masterclass, in which we talk about probably bounded suboptimal search, when data meets heuristic search. But let's take a short break now. Yes, you're still here. Thanks for that. I tried to save the best for last. Probably Bounded-Suboptimal search. To motivate these settings with a long name, consider the following plot, which was generated from data collected when solving the 15 puzzle. The x-axis shows possible ratios between h star, the optimal solution cost, and h. The y-axis is the percentage of states in this domain in which their actual h star over h ratio was the same or higher than the corresponding x value. That is, this plot shows the cumulative distribution of the relative error of the heuristic. The heuristic here was admissible, so h star over h is never smaller than 1. What this plot means, if you look at it closely, is that in 90% of the cases, the heuristic was off by more than 10%. So again, if the h of a node was x, with probability larger than 0.9, the actual cost to the goal was at least 1.1 times x. Again, putting this concretely, if your heuristic value was 46, most likely the real cost was 50. So, if I happen to find a solution whose cost is 50, there is high probability that this solution is already optimal. However, if I want to find an optimal solution, I would have to work hard to show that this solution is not 46, even though the probability that it is not 46 is only 10%. Sometimes this makes sense when optimality is really critical, but in many other cases, we'd much rather return a solution that is only probably optimal as long as we get this solution much faster. Similarly, we might be happy with a solution that is bounded-suboptimal for some W, say 1.1, even if there is a slight chance that this suboptimality is actually a little bit higher. We capture this intuition formally in the probably bounded-suboptimal search setting. In this setting, the input is a search problem, start, goal, end operators, a suboptimality bound W, but also a confidence bound delta. And the output that we want to get is a solution whose cost is x, where x is smaller than W times the optimal solution, with probability higher than 1 minus delta. This is a little bit complex, so let me put this in context. You can look at optimal and bounded-suboptimal search setup as special cases of this probably bounded-suboptimal setup. For delta equals 0 and W equals 1, this is exactly optimal search, and algorithms such as A star, IDA star, and others fall into that category. Similarly, setting delta equals 0 but W larger than 1 gives us bounded-suboptimal search. And then you can use algorithms such as weighted A star, EES, and dynamic potential search, which we've seen before. However, setting delta equals something that is larger than 0, for this we need something new. Or maybe not. Here is a simple framework to solve a probably bounded suboptimal search problem, which basically uses an anytime search in its core. This algorithm works as follows. First, run your anytime search algorithm of choice until it finds a solution. Then, check if this solution, which we'll term here best or incumbent, check if it is probably bounded suboptimal. If it is not, then continue the anytime search algorithm to find a better solution. And this iterates until we finally find a solution whose suboptimality is bounded with high probability. Simple, right? Well, the challenge is how to answer this question. How to answer whether a solution is probably bounded suboptimal. We propose a data-driven approach to address this challenge. In this approach, we collect statistics about the domain, by sampling states and solving them optimally. Specifically, we gathered statistics about the H star over H ratio. For example, these plots show the H star over H ratio for two standard search benchmarks, pancakes and vacuum cleaning. The different lines in each plot correspond to ranges of H values. We chose to create separate distributions for ranges of H values because we observed that different ranges of H values behave significantly different. For example, in the pancake puzzle, you can see that if the heuristic is equal to or smaller than 4, then it is almost always very accurate, while if it is between 4 and 8, it is highly inaccurate. But this is just one way to analyze the data, and other data analysis techniques are also valid. What is important is that we use these statistics to identify when a solution is probably bounded-suboptimal. But wait, I didn't explain how we do this. How do we use these statistics to identify when the anytime search in the framework we've seen before can stop? Several stopping conditions have been proposed that are based on these statistics. Let's look at one that is called the ratio-based stopping condition. It works as follows. It accepts the incumbent solution X, the suboptimality bound W, the confidence bound delta, and the gathered statistics about the H star over H ratio. Remember, what we want this stopping condition to do is to identify when X, the incumbent solution cost, is smaller than or equal to W times the optimal solution, with probability larger than 1 minus delta. This is just math talk for saying that X is probably bounded-suboptimal. Now, with some algebraic manipulation, we can take this probability statement and convert it to this. We basically divide it by W and the heuristic of the start state. Note that H star of the start state is actually the optimal solution. What is nice about this expression is the left-hand side is all numbers we can compute. We know X, we know W, and we know the heuristic of the start state. On the other hand, the right-hand side, this is exactly the variable that we collected statistics for. So we can just plug in the numbers on the left and look in the statistics we have collected to identify whether X is indeed probably bounded-suboptimal. There are other stopping conditions. Some are more sophisticated and consider also information collected during the search. However, I think at this stage, we are all tired and we would like to conclude. So I thank you all for staying all the way and listening to this masterclass. I hope I was able to show you that between optimal solution and any solution, there is a range of algorithms and settings in which, on the one hand, we can scale, but on the other hand, we can say something about solution quality. Also, I showed you that if you are able to improve and get a better bounded cost search algorithm, you will automatically be able to get a new bounded-suboptimal algorithm and a new anytime algorithm. And a new anytime algorithm would allow you to create a better, probably bounded-suboptimal algorithm. I think this is quite cool. There are so many hard and interesting challenges left to work on. We can try to learn the potential in potential search using machine learning. We can try to integrate search effort and not just the probability of getting to some node. We can try to look at different ways to sample the domain. Also, integrating inadmissible heuristics is likely to yield significant gains because such heuristics can be very, very effective and accurate. Also, adapting the search in other ways with learned statistics is an interesting challenge. One thing I want to end with, just to show the power of suboptimal search, is this slide, which is the results of experiments on a domain called multi-agent pathfinding. In this domain, we try to find paths for multiple agents. You can see the x-axis here is the number of agents. In general, the problem becomes exponentially harder as you add more agents. Now what I want to look at is the line corresponding to CBS. CBS is an optimal algorithm for this problem. While ECBS, the line here, this is a bounded-suboptimal algorithm for this problem. It uses a focal search. What you can see is that with CBS, we are able to solve problems up to 50 agents. while with ECBS we are able to solve problems with up to 250 agents. Again, remember the problem becomes exponentially harder as we add more agents. Now, I didn't tell you what was the suboptimality bound that we used here in ECBS. It was only 1%. So we were able to increase the number of agents from 50 to 250 by only allowing 1% of suboptimality. I think this highlights that using suboptimal search can give you huge gains while still having a strict suboptimality restrictions or a strict notion of how good your solution is. And I think before I end, I'd just like to note some of my collaborators over the years in several of these works, including Ariel Fellner and Meir Kalech, and Rob Holty, and Will Rummel and Rami Puzis, and Rick Valenzano. And I hope you enjoyed this. Feel free to contact me if you have questions in these topics or others.